The camera is mounted at a point 4,000 feet away from a geyser. If the water is rising vertically at 900 feet per second, when it is 3,000 feet above the ground, how fast must the camera angle of elevation change in degrees per second at that instant to keep the top of the water in the frame? So this is a classic related rates problem involving trigonometry because we're talking about angle. So I'm picturing this. We've got this angle here, this camera here, and it's pointed towards this geyser, right? The geyser is gushing water out here. So, and the water's rising, right? So this value is going up and up and up, and hence the angle is going up and up and up. So this angle is changing at a certain rate, and we're trying to find how fast it's changing in degrees per second. So the camera is 4,000 feet away from the base of the geyser. That's a fixed amount, not variable. This side is variable. This is something that's changing. So we've got our two variables are the angle and the height. So if I write an equation relating my variables, we see that that tangent is going to be the right one. Tangent of theta is h over 4,000. So for related rates, that's a 4,000. We want to take the derivative with respect to time. So the derivative of tangent of theta with respect to time is going to be secant squared of theta, but then times d theta dt, right? So I'm taking the derivative with respect to t. So this is my related rates. This is like differentiating implicitly. And then the derivative of h over 4,000 is just 1 over 4,000, but times dh dt, because again, I'm taking the derivative with respect to t. So now, once I've taken the derivative for related rate problems, we want to plug in all of the known values and solve for what's left. So we could try to fill in a bunch of values, but we only are given the height, right? We're looking at when the height is 900 feet per second. They don't seem to tell us what theta is. But we could do a quick little computation and note that when theta is here, when this is 4,000, and when the height is 3,000, we can solve for theta, because tangent of theta is going to be equal to 3,000 over 4,000. So we can solve for theta is going to be approximately, I'm working in radians, by the way, I should mention this. The question asks us to do this in degrees, but when we go to take the derivative and we say the derivative of tangent is secant squared, that's a fact in radians. Okay, if you were trying to take the derivative with respect to in degrees, you have a different coefficient out front. So I actually hate the fact that they're asking this for this question in degrees, but I'm going to do the entire problem in radians and then just at the end convert my answer. So this theta is in radians, and I use this theta, I plug that in for my theta here. I'm going to be taking the secant of that and squaring it. So that's some number here. That's times d theta dt, something I'm not expecting to solve for. I still have my 1 over 4,000. And then dh dt is given because they tell us how fast the height of the geyser is raising. So that's my 900. So everything's been plugged in that I know. I know my theta because of I knew h. I know then therefore secant squared of theta. I know dh dt. I know everything except d theta dt. So now it's just a little bit of algebra. Just algebraically multiply these two, divide by this, and so we get d theta dt. Sorry, the pen's doing some weird things here. We get 0.144 radians per second. This is how I would leave my answer if this were in a calculus class, but because they're asking for it in degrees per second, we want to convert that to degrees, and so that's going to be 8.25 degrees per second. So choice B is the correct answer.